Welcome to this video on modeling of palladium membranes. In this video, we will go into the mechanisms of mass transport that occur inside palladium membranes, as well as methods to model this behavior. Palladium membranes are used for highly selective hydrogen separation and find applications in membrane reactors with a remarkable performance. A palladium membrane typically consists of a dense palladium deposited layer and a porous support layer. The dense palladium layer is highly selective towards hydrogen. The support layer provides structure and stability for the palladium layer. Let us have a look at the membrane structure in more detail. Feed gas enters on the retentate side and travels through the dense palladium layer and porous support layer to the permeate side. The dense palladium layer is very thin, between 1 and 20 micrometers. This layer needs to be thin to ensure a sufficiently high membrane flux. The porous support is typically larger than 3 millimeters. The porous support layer is most commonly made of ceramic material, with a pore size between 0.1 and 1 micrometers. Ceramics provide excellent stability to the palladium layer and have little interaction with the palladium, making them a good choice as support. Another possibility is to use a metallic support, which consists of a metallic support layer and an interdiffusion layer. Metallic supports are cheaper than ceramic ones. They are more durable, and they can be sealed and connected more easily through welding. However, the metallic material interacts with the palladium. A ceramic interdiffusion layer is therefore required to avoid the palladium from diffusing into the metallic layer. A metallic support has an average pore size of 2 micrometers, and the ceramic interdiffusion layer has an average pore size of 0.05 micrometers. Scanning electron microscopy imaging shows a side-by-side comparison of a ceramic-supported and metallic-supported palladium membrane. The individual palladium and support layers can clearly be differentiated from each other. Membranes can operate in either a cross-flow configuration or a dead-end flow configuration, depending on application. For gas separation and membrane reactor applications, typically a cross-flow configuration is used. Permeation of species through a membrane requires a driving force. Hydrogen permeates through the dense palladium layer from a high-pressure retentate side to a low-pressure permeate side. In this example, the permeate side of the dense palladium layer starts at the interface between this dense layer and the porous support layer. As hydrogen molecules approach the dense palladium matrix on the retentate side, they split up into individual hydrogen atoms as they attach to palladium active site on the surface. This is known as dissociative adsorption. The split hydrogen atoms diffuse into the dense palladium layer with a solution diffusion mechanism. Finally, they recombine and detach through recombinative desorption as hydrogen molecules on the other side. The interaction of the palladium active sites with hydrogen, preferentially over other gases, results in very high selectivities and permeate side hydrogen purities over 99%. Permeation of hydrogen through dense membranes can be calculated with the Richardson equation, which describes the hydrogen permeation flux as a function of the permeability, layer thickness, and partial pressures to the power n. The permeability is described with an Arrhenius-type equation. Under the ideal condition of thermodynamic equilibrium between the hydrogen atoms dissolved at the membrane surface and the hydrogen concentration in the gas phase, the pressure exponent n becomes 0.5 and the Richardson equation takes the form of the so-called Sievert's law. According to Sievert's law, the diffusion of hydrogen atoms through the palladium bulk is the rate-limiting step in hydrogen permeation. After permeating through the dense palladium layer, hydrogen will diffuse into the support layer. Here, it experiences an additional resistance. As this support layer is porous, however, this resistance is generally speaking significantly lower than the resistance in the dense palladium layer. Permeation through a porous support layer can be described with a dusty gas model. This model states that the driving force for mass transport can be split up into multiple contributions. Specifically Knudsen diffusion, viscous flow, and molecular diffusion. Permeating species can experience an additional resistance at the external surface of the membrane. This resistance is referred to as concentration polarization. As hydrogen permeates through the membrane, it is depleted near the surface on the retentate side. In the presence of mixtures, this leads to an accumulation of the non-permeable species, resulting in an additional resistance for the hydrogen to reach the surface. Consequently, the concentration of hydrogen near the surface is reduced. This mass transport phenomenon is therefore referred to as concentration polarization. One method to describe this phenomenon is to implement a stagnant film model. This model assumes that concentration polarization creates a hydrogen-depleted boundary film on top of the membrane surface. The flux through this boundary film is then equated to the dense membrane flux on the interface between the boundary film and membrane surface. The membrane flux is again described by the Richardson equation. A Sherwood correlation is then used to calculate the mass transfer coefficient as a function of the characteristic size of the system and the mass diffusivity of hydrogen.